Two bits of homework we had last night, page 135, practice problems number 1 and 2, and we had page 136, check and reflect questions number 5 to 7. Take a look at 135 first of all. Any issues with questions 1 or 2 on page 135? Both of these are real similar to the example problem we did, right? Essentially, they were the same thing with different numbers. But if we need to go over one, we'll do that. Nobody? We're all good with those? All right, good, excellent. Let's take a look at the check and reflect questions that we had to do on page 136, then 5 to 7. Any issues with those questions on 136? 7, for sure. 5, okay. We got 5 and 7. 6, okay. 5 and 6, I think, were pretty similar, right, in terms of the way you do them. Different numbers, different directions, and so on, but pretty similar in terms of the method that you use to do them. So hopefully if we go over number 5 and anybody did have an issue with number 6, hopefully then that helps you a little bit with number 6. Let's take a look at number 5 here. It says 2 people, A and B, are pulling on a tree with ropes while person C is cutting down the tree. Person A applies a force at 45 degrees. Person B applies a force at 90 degrees, and we want to find the net force on the rope. Or sorry, at 345 degrees. We want to find the net force on the rope. Okay, so here's the object. Here's the tree, I suppose. Person A is pulling up at 45 degrees here, and we're going to say that's 80.0 newtons. We drew the diagram for this for you yesterday so that you knew that 45 degrees was above the horizontal axis there, and so that you knew that the 345 was 15 degrees below the horizontal axis. Okay, you don't ever need to worry about that notation. Okay, if you get a question like this on a quiz or on a test, I'll either give you the diagram or I'll tell you that it's, say, 15 degrees south of east or something like that. Don't worry about understanding the 345 and interpreting that 345. All right, we have to add these together to get the net force, but we have to do it in x and y components because it's not just x or y like the problems we were doing last week. It's x and y. But before we even do that, we've got to take a look at changing these funny angles into 90-degree angles. So in other words, we've got to redraw FA over to the side, get the x and y components of it. And we have to do the same thing with FB over to the side, get the x and y components of that one. Let's do FA over to the side here right now. FA is 80 newtons. It's at an angle of 45 degrees. This is going to be x. This is going to be y. Which trig function, please, do we use to solve for the x component? Which side of the triangle is it? Sadie, which side of the triangle is the x component there? Opposite adjacent or hypotenuse? Rucker, stop. Yeah. We're looking for the adjacent side. Good. We're looking for the adjacent side, so we're going to use the cosine function, which is adjacent over hypotenuse. Good. So we can say cosine 45 degrees is equal to adjacent over hypotenuse. That's x over 80. And therefore, x is equal to 80 cosine 45. 80 times 0.707, what does that equal, somebody? Bo? 56.56. Thank you. I'll do the same thing for the y component. Sine 45 degrees is equal to y over 80. And lightning fast calculations in my head here on this one, I'm going to say we're going to get about 56.56. Is that right? Boy, am I smart or what? Cosine 45 is the same as sine 45, right? So we knew it's going to be the same answer there. All right, let's take a look at the second one. It was FB, that was 90 newtons. That was an angle of 15 degrees, so the x isn't going to be the same for this one as y. Once again, it's the adjacent side of the triangle, so we're going to say cosine again. Cosine 15 degrees is equal to x over 90. What does x equal there? 90 times cosine 15. Anybody have that? 90 cos 15? 86.93. Thank you, Lane. And we're going to do the same thing for the y component. I'm not going to be able to do this one in my head so quickly. 90 times sine 15. Rucker, do you have that one? 23.29, thank you. All right, we've gotten rid of our funny angles basically now. We've got to go back to our original diagram here now and do those x and y components with F net is equal to the sum of the forces. So x, we're going to say F net is equal to the sum of the forces, F1, or FA I should say, plus FB. FA, 80 newtons, no. Once we get rid of those funny angles, we're never going to use that 80 newtons or that 90 newtons again. We're going to use the components that we just found in green and black there. FA we're dealing with the x component now, so the x component of FA is 56.56 newtons. Is it positive or negative? Positive or negative? Positive, good. Why is it positive? Good, because you're going to the right. Good, what about the next one? We're not going to use 90 newtons again. Once we've gotten rid of that, once we've found the x and y components of that 90 newtons is gone forever. We're going to replace that 90 newtons with which number here? 56, 56, 86, or 23? 86, right? And it's going to be positive as well because it's to the right. 86.93 newtons to the right. Let's add those up. 56.56 plus 86.93. 143.5. Hayden, is that exact? What's the exact number there? Do you have it? Okay. Mason, do you have that? 56.56. 103.143. 0.50. I don't think. Yeah, it's 0.49. Thank you, Cassie. 143.49 newtons for the x component. Remember, Hayden, we want to round to ideally to 3 or 4 or 5 decimal places, but at least a couple. Don't round it to 1 decimal place. Okay. Now, odds are, the odds are still about 3/4 to 1 in your favor that you're going to still get the question right, even if you round to 1 decimal place. But there's still about a 25% chance you're going to get it wrong as a result of that, so we don't want to take that chance. Okay. So let's do the y components now. Same basic idea. F net is equal to the sum of the forces here. That's FA plus FB. FA, what do we got here? FA, y components. FA, y components, what do we got for that one? What do we got for that one, Reese? FA for the y component. Object A right here. We replaced the 80 newtons with these two things right here in green, right? So which one of these is the y component? Christy, you have the y component of FA there? Right, 56.56. And it's positive value, right? It's positive because it's going up. What about the y component of the second one? How much of that 90 newtons right there, how much of that 90 newtons is y component? Yep. -23. Good. We're going to add negative 23.29. Brennan, why is it negative? Good. It's acting downwards. So we add these up. 56.56 minus 23.29. It's going to give me what? 33 point something. Thank you, Mason. 33.27 newtons, and it's positive. So our x component is to the right. Our y component is positive. It's up. So we're going to redraw this as a simple right angle triangle with 143 to the right and with 33.27 newtons this way. We're going to draw a resultant vector there, which is ultimately what we're looking for. This will be our net force. So the net force is going to be the square root of 143.49 squared. Don't forget to square that. I just gave a test this morning in Physics 30, period 1. It wasn't using the Pythagorean theorem. It wasn't using vector analysis. Part of it was, actually, but not the part that I want to talk about here. The part that I want to talk about using an equation for kinetic energy, which we're actually going to learn depending on how things go today, either today or on Monday. The equation for kinetic energy is 1/2 mv squared. Okay. As I collected the tests, I'm just real quickly looking through it, and out of about 22 people in that class, I bet at least 35–40% forgot to square the v. It's 1/2 mv squared. They went 1/2 mv and forgot to square that. Okay, that's just such a common mistake to forget to square things. Okay, when you see a square, you just ignore it. Okay, it's 143.49 squared, not 143.49. Okay, don't forget to square that. When we do this, square that, and then square root them, what do we get for f there? Somewhere around 150 or so. Okay, 147 newtons. Thank you, Josh. Now we got to do the angle as well. The angle, always drawn from the start of the vector diagram there, is going to be the inverse tan function of opposite over adjacent. What's the opposite side here, 143 or 333? Yes, 33. 33.27 over 143.49. Now, sometimes I look at this question, we look at the diagram there and say, you know, we can predict not exactly what the angle is going to be. We can predict the angle is going to be greater or less than 45 degrees. We're going over a long ways. We're going up a little bit. Is the angle going to be greater than 45 or less than 45? Yeah. Less than 45. And my guess would be it's going to be a fair bit less than 45 degrees. So we can't predict exactly what it's going to be. We still have to calculate it. But when we calculate it, we can at least look at it and say, okay, I think I'm right. Or, wait a second, I get 62 degrees. That can't be right because I predicted a number that was going to be less than 45 degrees. So what do we end up getting there for theta? Let's hope that we do get a number that's less than 45. All right? 13.05 or 13.1 to 3 digits. Good. And that would be, we're not really told, yeah, let's just say, because our frame of reference isn't north, south, east, west, let's just label it on our diagram 13.1 degrees and say that's our final answer. How many people got that? Okay. Good. Maybe we'll have a quiz coming up on that soon. Okay, maybe sooner than later. Not today. Couldn't have a quiz on that today. It's too late to do that today, but soon. All right, the other one we had to do was number 7, and this one is, I don't know about you guys, but to me this one is the tricky one. Number 5 is not necessarily easy, but it's more recipe-like, right? We know exactly what to do because we just follow a recipe and do it. Okay, number 7 is kind of a recipe, but we have to step outside that a little bit more. Okay, so let's take a look at this one. It says a sign that experiences a downward gravitational force of 245 newtons is suspended as shown below. Calculate the forces Ft1 and Ft2. Notice they're both at an angle of 55 degrees, and I think that's going to be helpful to me to know that they're both at the same angle. Let's draw a free body diagram. It's almost drawn now. I've got Ft1 drawn, I've got Ft2 drawn. But I've got one more force that I have to draw in, and of course, that's going to be gravity, right? And that's going to act straight downwards. Okay, let's label that as 245 newtons. We don't know how long gravity should be compared to the other two forces, so don't worry about its length. If you think real hard about it, you probably should know that gravity is going to be bigger than the other two forces. Now, you can make that prediction. It's a pretty solid prediction because, look, if there's only one force pulling down and there's two forces pulling up, the two forces pulling up get to split the work, right? So they're going to be less than the one force pulling down. But I wouldn't mark you wrong if you missed that a little bit. Okay, what we like to do at this point when we have funny angles like 55 degrees is to get rid of those funny angles. But since we don't know what Ft1 is or Ft2 is, we don't know what the magnitude of those forces are, we can't get rid of those funny angles right now. So let's just go straight to our x and y components. For our x component, we say the net force is equal to Ft1 x plus ft2x plus the x component of the force of gravity. ft1x plus ft2x plus the x component of gravity. Okay, it's no different than the last question we did, except that in this question, we don't necessarily know all the numbers to plug in there. We set it up the same way, though. Now, if this sign is at rest, and presumably the sign is at rest, right? Presumably the sign's not moving around, then tell me what the value of the net force is that acts on it. 0. An object at rest stays at rest until acted upon by an unbalanced force. The inference there, if it's at rest, it must be acted upon by no unbalanced force. The forces must balance. Okay, because if there were unbalanced forces, what would happen to it? It would either fall, or it would go up into the air, or it would swing to the side, and start moving, right? All right, so let's plug in a value of 0 for the net force there. ft1x, we don't know its value. ft2x, we don't know its value. fgx, well, we do know its value. How much of that 245 is in the x direction? How much of that 245 is left or right? This one's the easy one, right? 0. Well, now it's not overly useful to me or overly helpful to me yet because, as you can see there, we end up having two unknowns there. Right? ft1x and ft2x are unknowns. What you can see here is that ft1x, right, if we rearrange this to solve for ft1x, it would end up having the same value as ft2x. So we know that they're both going to be the same number. Now, having said that, we probably could have predicted that anyways, right? If you've got two angles that are the same, and they're both pulling up this object that's 245 newtons at the same angle, we probably could have predicted that they're going to be the same value anyways. Okay, so that's not helpful to me. Next, let's go to the y component and see if we can get something out of that one. Once again, for the y component, we'll say the net force is equal to ft1. This time it's ft1y plus ft2y plus fg for the y component. The net force, again, is 0 because it's at rest. Do we know the value of ft1y? We don't. We don't know ft2y either. But we do know the value of fgy. What's fg? Let's see if you get this. Okay, let's see if you get this one. Yeah? Bo? Good. Negative 245. Why negative, Bo? Good. Well, we still have two unknowns. Here's what I'm going to try here, though. If ft1 and ft2 are equal to each other, and we know they are, right? ft1x ends up being, when we rearrange this, equal to negative ft2x. Then let's try replacing ft2x with ft1x. That make sense? So in other words, instead of having ft1, the y component that is, instead of having ft1y plus ft2y plus negative 245, maybe we can try saying ft1y plus ft1y subtract 245. See what I've done there? I've just subbed in ft1y for ft2y. We know they're the same value. We know they're both acting up, right? For the x components, one's to the left, one's to the right. One's positive, one's negative. But for the y component, we know they're both up, we know they're both positive. They're with the same value. Then let's call them the same thing. That becomes 2 ft1y. Subtract 245. Let's take the 245 to the other side. Becomes 245 divided by 2, which is 122 Is that right? 122.5? How many people got this far? Good. So FT1Y is 122.5. So is FT2Y, because they're both the same. They're both 122.5. Now, I can go back to that diagram there. Look, we have FT1Y goes up this way, and the Y component there is 122.5 newtons. The angle right here is 55 degrees. I can find this. I want to say cosine 55 degrees is equal to adjacent over the hypotenuse, FT1. Not the x component, not the y component, rather just the overall. What do we get there? FT1 equals 122.5 over cosine 55. What's the answer there? Raise your question.
Just a question.
Yep.
55 degrees on the outside.
Isn't the 55 degrees where, sorry?
The other side. That's what the angle would be.
Yes, you're right, actually. Yep, you're absolutely right. Thank you. So the angle would, yeah, you're right. The angle would either be 35 if I drew it like this, or I could have just as easily drawn it like that, right?
Yeah.
Okay. But then if I drew it like that, it wouldn't be cosine anymore. It'd be sine because it's the y component. So 122.5. Thank you, Fraser. So let's make that sine. It doesn't make any difference whether you use the 55 or the 35. The 55 is no better than the 35 is there. I'm just using that angle because that's the way that it's drawn up there. So this becomes 122.5 divided by sine 55. And what do we get for that? 150? How many people got 150? Few people? Okay, good. Good. Let's take a look at this example that's up on the board here right now. What I want you to find in this example from this hanging sign is F2. Okay, get the value of F2. We know that this sign has a weight or a force of gravity acting down on it 300 newtons. We know that it's being pulled up at this angle of 173 newtons. Okay, I want you to find out how much the second rope has to pull it up by. Good? All right, let's get at it. Sorry, just a quick little typo there, guys. The angle of the second one isn't 30 degrees. I'm not going to tell you what that angle is. It's not drawn to scale, so don't panic about if you get an angle that doesn't seem to match up with that. Okay, it's not drawn to scale. Just solve for F2 based on what you see up on the board there right now, okay? All right, let's take a look up here now, everyone. This is not a great question. There's a flaw in this question, which means that if you end up doing it two different legitimate ways, you end up getting two different answers, and that shouldn't happen. Okay? If a question is well written, then you should find that no matter how you do it, as long as it's a legitimate way, you get the same answer. So we're not going to spend a whole lot of time on this question because of that. I'm going to put up another question in just a moment that's a better question, where you'll get the same answer no matter how you do it, which is the way it should be. The easiest way to do this here right now is to get the x and y components of that 173 newtons. So let's redraw the triangle. We got 173 there. We got 60 degrees right here. Okay, this is x, this is y. Let's say cosine 60 degrees is equal to x over 173. X ends up equaling 149.822. Let's find the y component by using sine 60 degrees. No, that's not right, is it? I just found the y component. The cosine should be, what is that? 173 times 0.5, that's 86.5? 86.5 newtons. Let's do the y component now. Sine 60 degrees is equal to x over 173. The y component ends up being equal to 149.822, right? All right, let's take a look at the x components and the y components now. Let's say for the x component, f net is equal to f1 plus f2 plus fg for the x component. F net is 0 because it's at rest. F1 for the x component is negative 86.5 because it's to the left. F2 for the x component is not known, plus 0 for fg. So that means ft2x is 86.5 newtons, if we rearrange that. 86.5 newtons. Now, let's do the y component, where we say the same thing, F net is equal to the sum of the forces, but this time it's F1y plus F2y plus Fg y component. 0 again, because it's at rest, it's suspended, is equal to F1y, which is, we found it was 149.822, and it's positive, plus F2y plus negative 300. And you solve for F2y here, it works out to be, what is that, about 150.17? No, it would be positive, actually, because on the right-hand side, we've got a negative number. 149 plus neg 300 is neg 150, and then take that to the other side, it ends up being positive. So what was it again, 150.17? So now let's combine those. We've got 86.5 newtons. We've got 150.17 newtons. And then we find the force on object number 2 using the Pythagorean theorem. And then we find that angle, of course, using the inverse tan function. Does that make sense? I think we're going to end up getting, what do we get when we do that? It's going to be 173, isn't it? 173 at 60 degrees? Okay. Is that what you get? No, it isn't. Okay, does that make sense, guys? Now, that's one way to do it. There is another way to do it that I'm not going to go through with you because it requires some mathematics that you've learned before, but that some of you probably aren't big fans of. So we're not going to do it that way. I'm going to put one more question up on the board. We're going to leave you with it, and that'll be your homework for Monday. And this one's going to work out no matter how you do it, as long as you do it legitimately. It's going to work out to be the same either way. So let's do this one, guys. Once again, we've got that sine. Hey, we're pulling the sine this way. We're pulling the sine this way. We got an angle of 30 degrees right there. We got a sine that has a weight, not a mass, a weight of 400 newtons. That means it's the force of gravity acting down on it. We're going to call this F1. We're going to call this F2. We want to find the values of F1, and we want to find the value of F2 as well. All right? Let's see what you can do with that for the next 5 minutes, and then finish it up for homework on Monday, okay? That's it.